Hi everyone. In this video I'm going to provide a walkthrough of growth curve modeling using Jamovi, and we will be relying on an example that is provided in Chapter 5 of Hox's text, Multi-Level Analysis Techniques and Applications. Before we get started, just note that underneath the video description you will find a link to the most recent edition of the book and the companion website. You will also find a link to the SPSS data file that I'm using, and you can read that data directly into Jamovi. I will also include a link to a PowerPoint related to this presentation. So for our example, we will be looking at changes in college students' GPAs over the course of 6 semesters. So you'll see in the data set that there is a variable that is called occasion, which is representing measurement occasion, and there are 6 semesters being represented. Now, instead of using codes of 1 to 6 for that particular variable, we are going to be using codes of 0 to 5. And the inclusion of the 0 in the coding will help us to interpret the initial status with respect to GPA. The data are in long format, so what that basically means is that you'll see that each row right here represents a given student's measurement on GPA at a particular time point. So you'll see that we have a student identifier, and the first 6 rows in the data set will be representing student 1 with that student's GPAs for the 6 semesters. So you can see that we have occasion variable. We have year 1, semester 1, year 1, semester 2, year 2, semester 1, year 2, semester 2, and so forth. So we have, again, GPA measured at each of those time points. We also have a job status variable, which is reflecting the number of hours worked during a given semester. So this will be included in our model as a time-varying covariate, or basically a time-varying predictor. Then we also have sex and high school GPA, and these are basically going to be included as time-invariant predictors of students' GPAs. So here I've opened up Jamovi, and the dataset has been imported from that SPSS data file, and so I'm just going to widen these columns a little bit so we can take a look at them. You'll see that we have a student variable. This is the student identifier, and what I'm going to do for this particular variable, I'm going to double click on it, and I'm going to change this from a continuous variable to a nominal variable. So you'll notice that sometimes when the program reads data in from another program, maybe the scaling of the variables is either lost, or maybe it's just not read in the way that you would want the variables to be scaled. So I'm changing this one to a nominal variable. The occasion variable, it's read in as nominal. You'll see over here, by the way, where it says levels, it's got basically the values for the variable right here, and it's got labels for the different levels for that particular variable. But for this demonstration, we're going to treat this variable as continuous, and for the GPA variable, it's read in as continuous. The job variable is read in as nominal, and we are also going to be treating this one as continuous as well. So you can see again here we have the value labels, and these are the actual values as they would appear in the data set. But again, we're going to treat this one as continuous as they do in the chapter. And the variable sex is appearing as nominal. It's coded 0 for male and 1 for female, and we're going to leave that alone. High school GPA is read in as continuous, and we're going to leave that as is. So the first thing that I want to do before we start running multi-level models is to just take a quick look at some of the students in terms of their growth trajectory. So I want to look at their initial status with respect to GPA, and then also look at the linear change over time for those students. So what I'm going to do is go up to data right here and click on filters, and you'll notice that a new variable is shown in the data set. It says filter 1. It's got a bunch of check marks, and what I want to do is I want to look at students 1 through 14, and look you can see right here that basically up to row 84, that's the last row for student 14 in terms of GPA. So in 85 it starts with student 15. So what I'm going to do is just go up here to where it says filter. I'm going to type in row and then 2 parentheses right here, and then I'm going to say less than 85 and hit enter, and you'll see that we have X marks showing up. So anything that I do in terms of analyses, what's going to happen is it's only going to be performed on those cases represented in rows 1 through 84. So I'm going to now go to analyses, go under exploration, and then click on scatter plot. So I'm going to move student down to this group variable box right here, and then I'm going to move occasion to the x-axis and GPA to the y-axis. And I'm also going to click on regression line. We're going to make this linear. So now you can see that we can visualize some of the growth trajectories, assuming a linear growth for students 1 through 14. And you can see that along the x-axis we have values of 0 all the way up through 5, and that's basically representing the semesters 1 through 6. So the 0 is reflecting the initial status, and you can see that we have evidence of variation between the students in terms of their initial GPAs. You'll also notice that the slopes for the regression lines appear to vary as well. So you can see some of the slopes are, all of them are positive, but you can see that some of them are more positive than others. So you can see this individual right here has a fairly weak linear growth, whereas you have this student right here that's exhibiting a very pronounced linear growth. So what that's telling me is that we do have some evidence of differences between students in terms of their initial status and their growth trajectories. So at this point I'm going to click on data and go back to filter, and I'm going to just right click and click on delete filter to get rid of that variable, so that now when I perform my analyses I can include all of the students. So now what we're going to do is start off with testing a null or no predictors model. So for this model, you'll notice that we have a level 1 equation. This is the first model, by the way, in Hox's presentation. So it's got level 1 equation. You'll notice that the subscripting, it's got a t and an I, and basically for this y right here, this would be the GPA at time t for student I. In other systems you might actually see the I appear first and then the t, but this is how Hox presents it. So you basically have student I at time t in terms of GPA is equal to this pi 0 I, and this is basically the average of a given student I's GPA across time. So then you've got plus epsilon ti, which is just basically representing a time-specific deviation for student I from that student's mean. At level 2, or the level 2 equation, you can see again we have the pi 0 I, so that's basically student I's mean GPA score over time is equal to the grand mean of all of the students' GPA means, if you will, plus the difference between student I's mean GPA from the grand mean of all the students' means, if you will. So you can see it's a mouthful when you're trying to explain some of this information. So at any rate, let's begin by running our analysis. So up here, what we will do is go under Analyses and then go under Linear Models, and we will click on Mixed Model. So we will move student down to the cluster variables box, and we're going to move occasion, we're going to leave occasion where it is, but we're going to move GPA to the dependent variable box. Now in Hox's presentation they use maximum likelihood estimation instead of REML, so I'm going to click off of this box right here where it says fixed effects. We're going to leave everything as is, including the fixed intercept. We're going to scroll down, go under random effects, we'll move the intercept over to the random coefficient. So we're specifying that there is variation in students, or rather across students, in terms of their GPAs. Down here where it says test, I'm going to click on LRT for random effects. This is the likelihood ratio chi-square test, which is basically going to allow us to test the variance in the intercepts. We're going to leave the effects correlation as is. It's not going to make any practical difference in this particular demonstration, but in other circumstances we might want to select not correlated versus correlated. Basically this is referring to the level 2 variance covariance matrix for any intercept or slope coefficients that are allowed to randomly vary across the higher level units. So looking at our output, you can see first off there's a box that contains model information. You'll see that we have AIC and BIC. These are most useful when you are trying to make comparisons between different models. Basically, models that have the lower AIC or BIC would be considered preferred over models with higher AIC or BIC values. And the nice thing about these indices is that it does not make any kind of assumption regarding models being nested. You'll also see there's a log likelihood right there, and then down below you can see R-square marginal and R-square conditional. These are pseudo R-square values. So these are Nakagawa's pseudo R-square values. Just keep in mind these are sort of analogies to OLS R-squares, so they're not computed in the same way. So just kind of keep that in mind when you're interpreting these. The R-square marginal really pertains to the effects related to the fixed effects in the model, and then the R-square conditional is considering both the fixed and random effects within a model. And given that this model does not contain any predictors, it shouldn't be any surprise that the R-square marginal is 0. Now as we scroll down, you can see that we have for the intercept, this is the grand mean of the student's means with respect to GPA. And remember that each student's mean, we have GPA that's averaged over time. So this is the grand mean of all of the students' means, if you will. And you'll notice that over here we have a t-test that's given, and this would be used if you wanted to test whether the intercept is significantly different from 0. Most circumstances that's not going to be of any kind of importance, so we're going to leave that off. Down here you can see that we have the student intercepts. So this is the intercepts that are varying across the level 2 units, which are their students. This is the variance estimate. This is the standard deviation of those intercepts. You'll see that we have the level 1 residuals that's given right here. So we have the standard deviations and the variance estimate for those level 1 residuals. The ICC is just basically computed by taking a ratio of the variance of the intercepts to the sum of the variances for the intercepts and the level 1 residuals. So this is useful for determining whether there's significant or substantial evidence of clustering in our data, and basically an ICC of 0 would be indicative of no clustering that's going on, which we would not expect that to be the case given that we have repeated measurements occurring within individuals. Obviously as values get higher, that means that there's greater evidence of clustering going on, and so this ICC right here is 0.368, so that's pretty substantial evidence. In the table that's below, you've got the random effect LRT. This is the likelihood ratio chi-square test, and if this is significant, then that's basically used to test whether this variance estimate right here for the intercept in this particular case is significantly greater than 0. And so if this is significant, that's going to indicate that we have significant between student variation with respect to GPAs, and that is obviously the case. Okay, so for our next model, we are going to be incorporating occasion as a fixed predictor of students' GPA. Now, occasion, remember that the initial measurement occasion is coded 0, which gives us helps us to interpret the intercept a little bit differently from what we had before. In this particular model right here, the intercept would be student I's initial status with respect to GPA. Then you've got the regression slope for the occasion variable, which is the pi 1i as given, and then you've got the level 1 residual that's given right here. The level 2 equations, now we have two of them. We have pi 0i, so again that's each student i's initial status on GPA is equal to the grand mean of all the students' initial statuses plus the difference between student i's initial status on GPA and the grand mean of those initial statuses. Then this next equation right here, the pi 1i, is equal to beta 10, which is essentially just the fixed effect for occasion. And so you could think about this as the grand mean across students with respect to the relationship between occasion and student GPAs. So if we were to substitute these level 2 equations into the level 1 equation, we would end up with this combined equation right here. So now let's go ahead and include our occasion variable as a predictor. So I'm going to move this down to the covariates box right here, and that's pretty much all we are going to have to do in this case. So you'll see with the model information, we've got our AIC and BICs. You can see that those values actually decreased relative to our previous model. In fact, just to kind of show you what we're talking about, if I take occasion back out just very briefly, you'll see that the values are 919 and 934 respectively. Including it, you can see that now we're down to 401.6 and 422. So we have decreases in those values. You'll see that the R-square marginal is 0.214. So you can see that previously it was 0. So this is a result of adding in the occasion predictor. When we scroll down, you can see that we have our fixed effects. So the intercept, this is the predicted GPA for semester 1 within the sample. This is essentially the grand mean of the initial statuses for all the students, which is 2.865, and then we have the regression slope for occasion. So it's positive and statistically significant, basically indicating that with each increment with respect to measurement occasion, we expect an increase in GPA of 0.106. Down here you can see our variance estimate for the intercepts. That's variance for the initial statuses for the students with respect to GPA, level 1 residual, and you'll see right here the ICC is actually increased relative to what we had before. And to be honest, most of the time as you're reading through the literature on growth curve modeling, that previous model with no predictors is not recommended as a baseline model. So if you want to use a baseline model and then incorporate subsequent models where you have predictors added and you want to make comparisons between models, this model is actually a better baseline model to use rather than that null or no predictors model. So you do see that the ICC is increased a little bit right here, and then when we go down here to the likelihood ratio test, testing the variation in the intercepts, basically the initial statuses for GPA, you can see that that is statistically significant. Now, one other thing that I forgot to mention, and which is that when you include predictors as covariates within your model in using Jamovi, if you go down under covariate scaling, you'll see that it says centered, and this is one of the defaults in Jamovi, so it can be a little bit frustrating because technically speaking I should have actually used the none option instead of leaving it as centered. So now things look a little bit different. So if you're making comparisons actually with what you see in chapter 5, these values will line up better than what you had before. So going back, if we look at the estimate for the intercepts is 2.599. That's the expected initial status for GPA across your students. You can see that the occasion regression slope is 0.106. And it's significant, so there's not really any difference there in terms of what we were finding before. You'll notice that there's our variance estimates for the level 2, the variance of the intercepts, as well as the level 1 variance. There's our ICC as before, and our significance test. So just kind of keep that in mind, that as you're adding in predictors in Jamovi, you really need to check out the covariance scaling in order to make sure that you have the predictors scaled as you intend. Okay, so for our third model, we are going to include the job status variable as a time-varying covariate, or basically time-varying predictor of GPA. So within this model right here, you can see that we're adding in at level 1, we have pi 2i multiplied by job status. So that's being included. And now, because we have that job status predictor included, we now have at level 2, our level 2 equations, we also have the fixed effect for that variable. So the pi 2i is equal to beta 20. And so if we substitute all of these portions of our level 2 equations into the level 1 equation, we end up with this combined equation right here. So going back into Jamovi, I'm going to go up here and click on Job and move it to the covariates box. And so you can see that as we're adding in the predictors, the covariates, you can see that under model terms, under fixed effects, they're showing up. Now, as I said before, by default, Jamovi adds in the covariates, or the predictors, as centered. So I'm going to click down here and go to none in order to remain consistent with the presentation in Hox's text. So now, as we're looking at it, you've got our model information. You can see we have more drops in terms of the AIC and BIC. So this would be considered a better model relative to the previous model. You can see the R-square marginal is a little bit higher than what it was previously. And as we're looking at our fixed effects parameter estimates, the predicted initial status for the model is 2.970. You can see that that's controlling for our predictors in the model. You've got the occasion variable right there. The regression slope is 0.102, and it's significant. So basically indicating that students' GPAs are increasing over time. And then you've also got this job variable right here. There's a negative 0.171, and you can see it's significant. So basically what this is telling us is that during semesters where a student works more hours, the predicted GPA is going to be lower. Here we have our variance estimate for the level 1 for the intercepts. The student level intercepts, or the initial statuses, controlling for the predictors in the model, and then the level 2 residuals, or excuse me, level 1 residuals given right here. The ICC is actually a little bit lower than what it was previously. And then looking at our likelihood ratio test, we still have evidence of significant variation in the initial status for students' GPAs. But just keep in mind that the initial status, we are controlling for the predictors that are included in the model. Okay, so now we're going to look at Model 4, where we are including our two time invariant predictors, sex and high school GPA. So our level 1 equation is going to be exactly the same as what it was previously, but now we're going to be including sex and high school GPA. So you can see I've got for predicting the initial status, for GPA, we have the grand mean of all of the students' initial statuses, but controlling for sex and high school GPA. So you'll see right here the regression slope is given as beta 0.1 and beta 0.2. So the 1 and 2 are reflecting essentially predictor 1 and predictor 2 at level 2 when we're trying to predict variation in the intercepts. You can see that we also still have our fixed effects related to the occasion variable and also our job status variable. So when we substitute our level 2 equations into the level 1, we end up with this combined equation that's given right here. So to carry out our analysis, I'm going to scroll back up and I am going to move high school GPA, I'm going to move, the high school GPA down to the covariates box, and I'm going to move sex over to the factors box. Now technically speaking, I could have used or move sex into the covariance box since it's a binary predictor variable. But I'm going to move sex under factors, which is going to help me out a little bit later when it comes to looking at some of the simple slopes when I'm looking at the interaction effect or the cross-level interaction. So I am going to scroll down here, and at this point under high school GPA, I'm going to go ahead and set this as none, just again to remain consistent with the text. Just keep in mind that there are different centering approaches that are available, but in Hox's presentation he does not use any kind of centering related to the high school GPA variable. Under factors coding, I'm going to select dummy, and there you go. So here you'll notice again, looking at the AIC and BIC, these values are decreasing. You'll see the R-square marginal has gotten a little bit larger as a result of including the predictors. And then down under fixed effects parameter estimates, the grand mean of the intercepts, basically reflecting the initial status for students' GPAs, controlling for the predictors in the model. You can see it's 2.6415. You can see our occasion variable, we have a positive regression slope. It's significant. You can see the job predictor, there's our negative regression slope. It's significant. So basically providing, again, evidence that over time we see significant linear growth with respect to GPA. That's inferred by looking at this row right here, and then we also see with the job status variable right here, because we have a negative coefficient, it's significant. We would interpret this to mean that students who worked more hours during a given semester were predicted to have lower GPAs. Then we have the high school GPA variable right there, and the regression slope, which is 0.0847. You can see it's statistically significant. And remember that we added high school GPA at level 2 to predict variation in the random intercepts. So what this would basically indicate is that students who had higher high school GPAs were predicted to have higher initial status with respect to GPA. Then our variable sex, you can see it's positive and significant, indicating that basically females were predicted to have higher GPAs during that initial semester than males. Kind of scrolling down again, you can see we have our variance estimates at level 2 in terms of the variance of the intercepts, level 1 residual variance, there's our ICC, and you can still see that we have significant variation in our initial status for GPAs by looking at our likelihood ratio test results. Okay, we're going to build on that previous model by now allowing the slope for the occasion variable to randomly vary. So if we do this, we're basically making the assumption that the linear rate of growth may itself vary across individuals. So you'll notice that we have our pi 1 I regression slope within the level 1 equation. What we're going to do is at level 2 we are going to keep our beta 1 0, which is essentially treated as an average of the effect of the occasion variable on GPA across all of the individuals. But now we have the mu 1 I, which is reflecting the difference between a given student's linear growth trajectory and the grand mean of the students' growth trajectories. So basically this is the only addition that we're including in this particular model. But now with the combined equation, you'll see that we have right here, there's our beta 1 0 multiplied by occasion right there, and then you can also see that we have mu 1 I multiplied by occasion. That's through our substitution of our level 2 equations into the level 1 equation. So now what we're going to do is go up, and where it says random effects, we're going to move the occasion predictor over from the box on the left to the box on the right. And so now we have a variance estimate for the intercept, the slopes, and then also the level 1 residuals. So this is essentially our variance estimate for the intercepts. We have the variance estimate for the slope, which is occasion, and then we have the variance estimate for the level 1 residuals. Now you'll notice that over here where it's got effects correlation, we haven't touched this up to this point, and that's because we were only estimating one variance at level 2, and that was the variance of the intercepts. And so because this is left as correlated, what this is going to do is allow, or basically yield, an estimate of the correlation between the varying intercepts and slopes across the students at level 2. So this is the correlation between the intercepts and slopes. So you can see it's got param 1 and param 2 right there, intercept, and then the occasion variable. So you can see that the intercepts and slopes were correlated at roughly negative 0.21 across the students. And now if it's the case, and by the way, so under random effect LRT, now this is basically a test of the combined variation in the intercepts and slopes. So that's why you got the degrees of freedom of 2 right there, and you can see it's statistically significant. Now let's say that we wanted to not estimate a correlation between the intercepts and slopes. Basically we can do that by just clicking on this button right here for not correlated, and when we do this you'll notice that now we still have our variance estimates for the intercepts and the slopes, but now you've got a unique likelihood ratio test for each of those random components. But we're going to go ahead and stick with the presentation in Hox's text and leave the effects correlation set at correlated. Okay, for model 6, this is the final model that is presented in Hox's for this particular extended example. And now what we're going to do is we're going to add sex as a predictor of the variation in slopes at level 1 for the occasion predictor. So you'll notice that now our pi 1i regression slope, this one right here, we have it set equal to the beta 10, that's the grand mean of the regression slopes. We also have our mu 1i, which is reflecting the variation in the regression slopes. But now we are including sex as a predictor, and you'll notice that we have a regression slope for beta 11. And multiplied by sex. So in this particular case, what we're essentially modeling is the variation in the level 1 regression slopes for occasion as a function of sex. Now you'll notice that our combined equation gets a lot more complicated when we are now including predictors of varying slopes. So when we substitute our level 2 equations into the level 1 equation, you'll see that this is the final equation after we've kind of reorganized everything. You'll notice that beta 11 is being multiplied by sex by occasion. So that's an interaction term reflecting the cross-level interaction between sex and occasion. So we can treat sex as a potential moderator of the linear growth rate at level 1. So to accomplish this, what I'm going to do is go under fixed effects, and I'm going to highlight sex and the occasion variable right here, and click on this button right here, go to interaction. And when I do that, you can see that now our table includes an interaction term. So it's basically down here. There's our interaction term, our regression slope, and you can see that we have statistical significance. So at this point, it looks like we have evidence that perhaps gender or sex is a significant moderator of the relationship between the occasion predictor and students' GPAs. If I want to probe that interaction, I can scroll down and basically go under plots. If I would just want a plot of the interaction, I can click on occasion. I'm going to move it to the horizontal axis and then move sex to the separate lines box, and you can see under effects plots it's going to show up. There it is. And so it looks like that just visually it appears that among males the the linear rate of change over time is weaker than it is for females. The females are this orange line right here, and for the males that's the blue line right there. If I want to test those simple slopes, I can also do that really simply by clicking under Simple Effects, and I'll move Occasion over to the Simple Effects Variables box, and then Sex over to the Moderator box right there. And you'll see that it kind of takes a second to think, but now you can see the regression slopes of 0.0878 for males. That's is basically indicating a positive and significant relationship, and then for females it's 0.1174, and we have basically indicating a positive and significant relationship. But it does appear that there is a difference between these two slope estimates, and that's basically what's being tested when we are looking at the test for the interaction effect right there. Now, one last thing before I wrap up, I do want to mention that the current version of Jamovi, right now I'm working with version 1.2.2. It does not allow you to specify different covariance matrices for the residuals at level 1, as you would be able to with SPSS or Stata or some other programs. As such, the assumed covariance structures for the residuals is going to be a scaled identity, which assumes that the level 1 residuals have equal variances and that there is zero covariance among the repeated measurements, or at least the residuals from the repeated measurements. And in fact, I just went ahead and just kind of changed that up here just to make sure it's a little bit clearer. So basically we're making the assumption that the residuals are not correlated across the repeated measurements. And this may or may not be a tenable assumption with your data. So just kind of keep in mind that if you are assuming a more complex error structure at level 1, then you might consider using a different program, at least until Jamovi comes out with a version that allows for that specification. So at any rate, that concludes this video presentation, and I thank you for watching.